Today's topic deals with electric fields and electric potentials. And this is really where the mysterious nature of electricity comes into play. Lightning has mystified people throughout the ages, and probably the first human to really fully understand the nature of electricity is this guy right here, Nikola Tesla. Here he is holding a light bulb that's being lit, and there's no hidden wires. It's just being lit by the electric field that he has placed himself into. Um, so imagine 100 years ago seeing this photograph, and I certainly would have been mystified. So electric fields are basically a field that fills the space around every charge. So it's the electric field of the proton that keeps the electron orbiting it in perpetuity, just as it's the gravitational field that keeps a satellite orbiting it. So it's kind of an aura that extends out through space around any charge. So everybody's familiar with these Van de Graaff generators, these big metal domes that somebody can put their hand on and then their hair stands on end. But what a lot of people don't realize is that there's a field surrounding that, just the space around the Van de Graaff generator, so that if you were near it, that electric field could charge your hair and cause it to stand on end. Okay. So these field lines, by convention, we say that the field emanates out of a positive charge into a negative charge. And if we take a positive and negative charge and put them near each other, then the field would orient thusly. And if we have a flat plate positively charged next to a negatively charged plate, then the field lines would go straight across thusly. Okay, now we can visualize these with tiny, tiny oil droplets, and these are oppositely charged uh, conductors. And you can see the field lines orienting just like they're diagrammed here. And if you look closely, you can see that these field lines are repelling each other. So what can we say about these conductors? Well, we only know that they're like charged. We don't know whether they're both positive or both negative, but we can see that they're repelling each other, so they must have the same charge. And then here are those flat plates, that, like here. And then an interesting thing, as you saw in the video lab that we did with static electricity, that in a hollow conductor or inside of a conductor, there is no field. So the field strength would be zero. So this leads to an important principle known as electric shielding. So electricity, electrons will spread out on the surface of a conductor such that the field strength inside is zero. So you can see that if it's a spherical conductor, they'll be evenly spaced. But if it's angular, then the charges concentrate near the points. Even if it's spherical and kind of egg-shaped, they'll concentrate in the pointy part of the egg. So if you have a lightning rod that's pointy, then the field strength is going to be greater at the point. Now this is important. There are many electronic devices that have metal housings around the important electrical components, so that any other stuff that's going on outside that's electrical in nature will not cause interference between it. Um, and if you're in a lightning storm, you don't want to run out in the middle of the field like a lot of people think. You want to stay in your car. As this is illustrating here, the person in this car is perfectly safe. They wouldn't want to touch anything metallic, or you wouldn't want to be on the surface of the car, but inside the car, the field is zero. Okay, so this illustrates the similarity between gravitational potential energy maximum potential energy here, maximum kinetic energy here. So the energy is conserved. It's being transferred, converted from potential to kinetic. So here we have maximum potential energy here and maximum kinetic energy here. Okay. Now, there's a couple of terms that are really, unfortunately, worded, kind of like back in the heat unit. Remember specific heat and heat capacity, um, and, and even heat. All similar things, all related but different. So we have electric potential and electric potential energy. Now, the word energy here should help you out. We know about energy from prior units. We know that energy and work are similar. They can do energy can do work. So this electrical potential energy is just like any other potential energy, but it's electrical in nature and it's based on electric charges. So electrical potential energy is the energy an electric charge has by virtue of its position. So it depends on the type of charge, whether it's positive or negative, the amount of charge, and the strength of the field that's produced by it. Okay. So here we have a large sphere, maybe a Van de Graaff generator, and then a single positive um, point charge, and it's going to gain potential energy because it takes work to push it closer to this light charged sphere. So um, here we have two charged objects. They're the same distance away, so they would have um, the same voltage. And I'm getting a little ahead of myself. So let's talk about what electric potential is. So electric potential is the amount of electric potential energy per unit charge. Okay, so the amount of charge is important, and it depends on the amount of charge and the distance from the charge. So the electric potential is the electric potential energy, which is what we just talked about, which is measured in joules per unit charge, which is measured in coulombs. So if we look at these two objects, they have the same voltage because they're the same distance away, and this has the same charge for each. But this one has more electric potential energy because it has more charge. Okay. Now, if you take a balloon and rub it on your head, you're going to be conferring electrical energy to that balloon. And it might surprise you to hear that it would be 5,000 volts, but it's not dangerous. You're not going to get shocked. It would have enough energy to hold itself against the wall. But if you think about how much gravitational potential energy does a balloon have, well, balloons are pretty light. So how much electrical potential energy does it take to hold it against the wall? Well, it's not very heavy, so not very much. So the electric potential energy that you conferred to that balloon is only about 1,000th of a joule. But the amount of charge is only 1,000,000th of a coulomb. So 1,000 divided by 1,000,000 is 1,000. Okay? So you can have a high voltage object, but if it has a low charge, then that's how it got its high voltage, because it's a very small denominator. Now, storing electric charge, to make it useful, batteries are probably the most common way, but in many electrical devices, we want to be able to use the electrical energy instantly. Okay, so a capacitor is a device that stores charge in a circuit and makes it available instantly. Okay, so it's made by having a voltage source, um, and on the positive pole you hook up a plate, and the negative pole you hook up a plate. Now this would be really clunky, So what they do is they put an insulator in between them and then they wrap it. Okay, so that you have negative and positive here, easily accessible. You can hook wires up to this. So here's a bunch of capacitors of various sizes. They come down even tinier than your pinky and get as big as, oh gosh, like a soda can or something. Um, so they're used in all kinds of electronic devices, from on-off switches. They're used in computer motherboards, photo flash units, for cameras, not the ones in your phone, although I imagine there would be capacitors in your phone. Computer keyboards, every one of these keys down here has a little tiny capacitor on it that when you hit it, it disperses the charge instantly to the computer, telling that the G key was just hit. So calculators, photocopiers, electrostatics is used to make photo printers or computer printers, and then also in lasers. Okay, now I'm going to ask you to either pause the video and read this to get a better appreciation for how printers work. And if you think about what we have taken for granted, that we can get an instant printout of all this information in exactly the right place, in exactly the right color, all using static electricity. It boggles the mind. And then this is a little working of the Van de Graaff generator. The fellow on that video that I had you watch talked about a rubber band that rotates, and then the friction between it and the rollers cause a production of static buildup, similar to you walking across the surface of a carpeted floor on a really dry day. And then that buildup is transferred to the dome and spread evenly throughout. And then all kinds of funny and interesting and mysterious things can happen because of the